So now let us look at another mechanism of broadening. So imagine we have a collection of gas, just like we had in the previous scenario where pressure was the cause for broadening. So let us look at a scenario where pressure is not a dominant phenomena. So the pressure broadening is negligible. Think of a collection of atoms wherein collisions are not as many, yet the atoms are in thermal equilibrium and they are moving back and forth within the gas set. So the phenomena that we are going to look at is very different from the collisional broadening. This is called the Doppler broadening, wherein the physics of uh, this broadening mechanism is completely different from what we have seen earlier. So what you have here is an atom moving with a certain velocity, and you see that because of its motional degree of freedom, the frequency of the oncoming radiation is shifted due to the Doppler effect. So for example, imagine that um, I have a frequency source who's got an optical frequency nu, and you have an atom. An atom is moving with a velocity v. Of course, we are in the regime where v is much, much smaller than the speed of light. And you see that for such a system, the apparent frequency, right, which is seen by the atom, nu prime, is the original frequency at which the light is coming, and this light is because it's the light as well as the atom are moving in the same direction. You see that the frequency is redshifted, and what the atom observes is a frequency which is lower than the original frequency that is impinged on it, right? If the velocity is reversed, of course, you would see that rather than a negative sign, you will have a plus sign within the bracket. And this is what is known as the Doppler effect. So clearly you see that the frequency as seen by the atom depends on its velocity. So what we want to obtain, what is the velocity distribution of atoms that you have at thermal equilibrium? This is given by something called the Maxwell-Boltzmann distribution. These are both names that have been at the heart of developments in statistical mechanics. So the Maxwell-Boltzmann distribution gives you the following. So the fraction of atoms df with a velocity v is simply given by this quantity. M is the mass of the atom, 2 pi, and K is the Boltzmann constant, T is the temperature in Kelvin. This is a normalization factor, and essentially it is a minus M, let's say Vz square by 2 kt dvz, and what I mean is Z. What this is telling you is basically fraction of atoms which are moving along the Z direction, which is the direction in which we are going to put our light beam. Fraction of atoms who have a velocity between Vz to Vz plus dvz, right? So within this range, this is the fraction of atoms uh, among the collection. Let's just dwell on this equation. You see that this is like a Gaussian function. So if I plot Vz, right, on this axis, and Vz being a vector, uh, it can take both positive and negative values. So you see that this is clearly a Gaussian function, right? and one can see that this exponentially decays on either side of this. And the width of this is essentially given by uh, the temperature, right? The temperature of the gas and the mass of the species, mass of the atom. You should not be surprised that the maximum number of atoms are actually residing at Vz equal to 0, right? And there is no preferential direction, so positive and negative Vz's are equal, right? It's symmetric about that. And you should expect that Vz equal to 0 has the maximum atoms because you see that the velocity is actually random. So Vz equal to 0 is that fraction of atoms which have got components along the two perpendicular directions, which is x and y. This fraction of atoms is moving in that two-dimensional plane in comparison to this one-dimensional distribution. Clearly, those will be more, and hence this is indeed peaks at Vz equal to 0. If you look at the same atom from the perspective of the light, so I had the same situation where both the atom and the light is in the same direction. For the same situation, imagine that the atomic resonance was nu naught. This is for the stationary atom. From the perspective of the light, what has happened is because the atom sees the light as redshifted, from the perspective of the light, one can think of it that the atomic resonance itself is blue shifted. So you need to just give it a thought. So this would be the frequency, you know, of the absorbed light. So let me just repeat myself. Uh, in this scenario where you have the light and the atom both in the same direction, both light, the atom is moving at v, the light is of the frequency nu. So you see, from the perspective of the light, it appears as though the atomic frequency itself has blue shifted. It is the Doppler shifted light that is going to be absorbed. Equivalently, one can think of that the atomic resonance has Doppler shifted because of the atomic motion. Right. So once you have that, what I want to do now is basically convert uh, this equation. Let me call this velocity distribution as equation number one. I want to convert this equation into the distribution of frequencies, because after all, the frequency tag can be uniquely associated, the frequency shift can be uniquely associated with the uh, velocity Vz along the z direction which we are talking about. So I can rewrite my equation. So V equal to, so I'll just nu minus nu naught. This is just follows from this equation, uh, times C by nu naught, right? So if I now look at its differential, so by V I mean everywhere Vz. I've just dropped it for the sake of clarity. So my dV is indeed C V naught nu naught times d nu. So you see that I can use these relationships, that is equation number 2 and equation number 3 in equation number 1, no, and then I can arrive at this frequency dependent df, now of now a function of frequency is simply, so all that I'm going to do is replace my Vz square by the equation 2, right? So this is going to give me minus mc square by 2 nu naught square kt times nu minus nu naught whole square multiplied by c by nu naught, that is my dv element, and this is d nu, right? So you see, I can write down this as a line shape s of nu, which is given by this following. I'll just collect all these terms together. Mc square, put this back into, put this term back in here. So I have mc square, right? And clearly this satisfies all the properties of a distribution. Remember, what was the property? I have that my integral over the distribution s of nu d nu should give me 1. So let us check this out. So I'm writing the prefactor as simply s of nu naught, and this is integral from 0 to infinity exponential minus mc square nu minus nu naught whole square divided by twice kt nu naught square d nu. Let's make a change of variable. Let me call nu minus nu naught as let's call it mu. So my d nu is d mu, and when nu equal to 0, I'm looking at now the limits. This implies that my mu is minus nu naught, and when nu equal to infinity, of course, implies that mu is infinity. So putting all these together, I can equivalently write this as s of nu naught minus nu naught to infinity exponential minus mc square mu square divided by 2 kt nu naught square, and this is d mu. Now we know that nu naught is, so I'd like to note two things. Let me write that in a separate color. So the first thing I want to note is that my nu naught is large. So in my limit of minus nu naught can be equivalently replaced by minus infinity. The second important thing I want to look at is just the integrand itself. So you see that kT, which is the temperature, the energy associated with the thermal temperature, is much smaller than mc square at mu equal to minus nu naught, right? The integrand is negligible. So given these two scenario, I can as well write down my s of nu as s of nu naught, that remains, and this is simply minus infinity to infinity exponential minus m c square mu square by 2 kt nu naught square d mu. And you know how to do these integrals, which are just Gaussian, right? This is simply, if you do this integral, you'll see that this is simply square root of pi by the rest of the factor, right? Which is m c square divided by 2 kt nu naught square. And I want this integral to go to 1. That just gives me precisely, you know, that factor. So my s of nu naught, now this is my coefficient uh, of my distribution, right? Normalization coefficient is 1, right? Because this is minus this is same as 0 to infinity s of nu d, right? So this is our, so this is important normalization condition. And so you see, I can write down my s of nu in the, obviously this distribution peaks at nu equal to nu naught, right? Which would be the nu naught would be then the atomic resonance frequency for a stationary atom. Um, and you see that I can identify delta nu Doppler as the Doppler width, and by this I mean the full width at half maxima, right? This Doppler width can be written in this form. It is 2 nu naught. I'm just identifying it from the exponent itself, 2 nu naught by c. And this is 2 kt by m, and this is log 2. Why did I include this log 2? You will get the logic soon. So I can write down my S of nu as, this is my sort of the final form, 1 over delta nu Doppler square. So why I've included log 2 is to ensure that my S of nu naught plus minus delta nu Doppler by 2, right? This is my full width of maxima. At these values, I should simply get, what I would get is S of nu naught times exponential minus log 2, right? Which is same as S of nu naught by 2, right? So this simply ensures that I'm looking at the full width at half maxima, and that is why I have introduced this these notions. So what I want you to clearly understand is the following: that the Doppler width uh, clearly depends on a few parameters, and these parameters are important. The Doppler width is going to be larger. For example, if I'm looking at the same atom, if I'm looking at a transition which corresponds to a higher energy difference or higher frequency, that will suffer larger Doppler width in comparison to a transition where nu naught is smaller. The second important thing is that as temperature increases, the Doppler width increases. So the mass of the atom, it depends inversely on the square root of the mass of the atom itself. So these are the three quantities on which the Doppler width depends. And clearly it has the same behavior that we know earlier. The normalization factor itself contains this 1 over nu Doppler kind of a thing. So clearly you will see that if I plot two different distributions, right? This is, let's say, for Doppler width 1, and clearly if I plot the second distribution, right? So you will see that this Doppler width and this Doppler width is significantly different. This is delta nu Doppler 1, let us say, and this is delta nu Doppler 2, right? Clearly you will see that uh, delta nu Doppler 2 is larger than the delta nu Doppler 1, right? So larger the Doppler width, the the interaction at the line center comes down, right? So this maximas are inversely proportional to the Doppler width itself. So the maxima comes down and the width of the distribution increases, uh, just like we have seen earlier. So one can now, just like we had done in terms of atomic parameters, rather than having the absolute mass of the atom, one can look at the atomic mass, right? So one can rewrite this Doppler width in a following form. This is a very practical formula which you can use to calculate the Doppler width. So delta nu Doppler is given by 2 by lambda naught twice the gas constant, universal gas constant RT. M is the molecular weight of the corresponding atom, and square root of this. Let me just, as an aside, for completeness, let me, I want to determine the value of this integral I, which is simply the Gaussian integral, exponential minus, let's say, ax square dx, right? I want to determine this. So there is a neat trick that we use without trying to remember what the result is. And the trick is this: we consider I square, right? Which is, I'm simply writing down the same uh, into a double integral. So it's exponential minus ax square dx multiplied by exponential minus a y square dy, right? So I can rewrite this I square as minus infinity to plus infinity for both of them, and this is exponential minus a x square plus y square and dx dy. Clearly you will recognize that this is a two-dimensional integral which I can make a transformation from the Cartesian coordinates to the polar coordinates, and I can write down this as 0 to 2 pi uh, and 0 to infinity, and this is going to be exponential minus a rho square rho d phi d rho. You see the transformation? Remember that rho square is x square plus y square, right? This is my radial distance in a cylindrical polar, if you like. And my phi is simply tan inverse y by x. So you see that my uh, the dx dy element can be actually be written in terms of uh, rho d phi d rho, right? So putting all of that together, I can undertake the integral for phi. So that gives me 2 pi. And then I have left with 0 to infinity exponential minus a rho square rho d rho. You can quickly make uh, a substitution that my rho square is t 2 rho 2 rho d rho is my differential, that is dt. So I can rewrite this as 2 pi dt by 2 here. So this 2 gets cancelled, and now I can integrate this, and this simply becomes minus pi by a exponential minus at integrated from 0 to infinity, which gives me pi by a. So you see that my I now becomes square root pi by a, which is precisely is the value of this integral. So this is a neat trick that one uses by transforming it from Cartesian coordinate to polar coordinates. All right. So anyway, coming back to our business of Doppler broadening. Remember that the physical mechanism is what dictates the line shape. Very unlike the previous scenario where we had a Lorentzian, which should have long tails away from the resonance frequency. What you have here is an exponential distribution. There is an important idea that I want to raise now. This is got to do with understanding the nature of broadening. So there are two types of broadening mechanisms. One is called the homogeneous broadening mechanism, and the other one is a inhomogeneous broadening mechanism. And by this, what I mean is the following. So by homogeneous, I mean that every atom identically suffers the same broadening mechanism. For example, one can talk of spontaneous emission, right? Now, spontaneous emission is equivalent for every atom. Every atom suffers exactly the same spontaneous emission lifetime for the collection of atoms that we have. And so spontaneous emission would lead to what we call as a homogeneous broadening mechanism. Another example for homogeneous broadening is, for example, what we already seen, collisional broadening. In the collisional broadening mechanism, there is nothing special about a particular atom. All atoms in this collection statistically experience exactly uh, equivalent number of collisions, and hence the broadening effectively is uniform for the whole collection of atoms. Right? Collision broadening is a homogeneous broadening mechanism. In contrast, let's compare with the inhomogeneous one. So this Doppler broadening is clearly an inhomogeneous broadening mechanism. Why is that? Because you see, Doppler broadening depends precisely on the velocity of the particular atom. So in principle, I could have distinguished between my collection of atoms by putting on them the tags associated with their respective velocities. The atoms having a particular velocity can be associated with a resonant frequency which is shifted to that extent. Another set of atoms which are moving with a different velocity will have their resonance shifted differently. So in principle, I could distinguish in my statistical distribution, I could distinguish between atoms who have got a tag associated with that of their velocity. And hence, this is an inhomogeneous broadening mechanism um, where velocity of the atom becomes the physical tag that distinguishes all equivalent atoms, but they have become different because of uh, their velocity. Uh, uh, Such a distinction cannot be made for homogeneous broadening, where I cannot put a tag on some atoms being different from other atoms because all of them suffer the same broadening mechanism. So the Doppler effect actually leads to inhomogeneous broadening. The other examples of this could be, broadening due to the crystal local fields leads to broadening mechanism. Imagine I take a ND YAG laser. Um, the active medium is ND YAG. What you have is a YAG crystal, which is yttrium aluminum garnet. This is a transparent matrix within which neodymium atoms are doped. What you are going to get is in principle a inhomogeneous broadening mechanism where even though you began with a collection of neodymium atoms which are identical on doping, they experience different local fields, thus having a different frequency shift arising from its local position within the crystal. So these are two important things that we need to keep in mind. And very interestingly, uh, we find that all homogeneous broadening mechanisms actually lead to a Lorentzian line shape. And there is no mathematical proof for this. So this is one interesting problem that you can pursue and see if you can obtain a proof that tells you that if the mechanism is homogeneous, then the line shape is going to be Lorentzian. So on that interesting note, I would end this lecture.